So the various branches of science overlap, and so here chemistry is going to take a little field trip into physics. So we need to talk about light, and what is light? So light is a form of electromagnetic radiation. It's composed of perpendicular oscillating waves. One is an electric field, and one is a magnetic field. So an electric field is a region in which an electrically charged particle would experience a force, and a magnetic field is a region where a magnetized particle would experience a force. Electromagnetic waves move through space at the same constant speed. Light is electromagnetic radiation. Electromagnetic radiation moves at the speed of light. It all moves at the same speed, and that speed is 3 times 10 to the 8th meters per second. It's pretty fast. So here's an illustration of electromagnetic radiation, and we've got the electric field component is oscillating in the vertical plane, and the magnetic field component is oscillating in a horizontal plane. Both of these fields are moving in the same direction at the same speed. So here we have a photograph of lightning striking a building. And we see the lightning. So what we're seeing is light from this event. The light moves at the speed of light, 3 times 10 to the 8th meters per second. Later, we hear the sound from this event that we call thunder. Sound moves at a slower rate of speed, only about 340 meters per second. So we see the lightning and we hear the thunder later, and the delay between them depends on how far away we are from that event. And so this is where the estimation of how far is the center of this storm away from me. Well, you can count the number of seconds between the lightning and the thunder, and that will give you an estimate of how far away the storm is. If it's very close, like if the lightning strikes the building next to you, the lightning and the thunder will occur simultaneously. If it's miles away, you see the lightning, and then several seconds later you hear the thunder, because they travel at different speeds. Any questions about that?
So they're actually happening at the same time?
They happen at the same time, yep. But you just don't get the information at the same time. I don't know if you've ever noticed this. If you're in a big auditorium or a big stadium, and you've got someone way down there and they're speaking, you see their mouth moving, but the sound comes slower, and so it's a little out of joint. And if the sound system isn't set up correctly in the stadium, you can get this weird oscillating thing where the sound is coming to you at different times, and it can sound very, very strange.
So in Grand Central Station in New York, where one person sat at the end of the train station, one person would be at the other end, the sound that they project across the ceiling. How does that, is that the same idea?
Well, that doesn't have to do with the speed of it. But yes, there are places like Grand Central Station where the geometry of the space is such that the sound waves are bounced efficiently from one place to another. And so you can stand in one spot and say something, and the sound waves are directed and collide again in a small space on the other side. And if you're standing there, you can hear it clearly, even though people in the middle can't. Yeah, that's physics. Physics is fun too. Any other questions? So we can measure different things about light to characterize it. And this works for all types of waves. We can measure the amplitude. So the amplitude of a wave is how high it is. Waves go up and down. And so there's a midpoint here, and it goes above the midpoint, and below. And so here we're measuring how far above or below it goes, and that's the amplitude. We can measure the distance from one crest to the next crest, and that's called the wavelength. It's the length of a wave. That is given the symbol lambda, so Greek lowercase l. The amplitude corresponds to how intense or how bright the light is. If the amplitude is large, the light is very intense, it's very bright. The wavelength we perceive as different colors. So here we have illustration of 3 different wavelengths. These all have the same amplitude. The height of each wave is the same. But this one has a very long wavelength. The distance between one crest and the next crest is longer. This one's in the middle, and this one's the shortest distance between these 2 crests. So our eyes and brains perceive differences in wavelength as different colors. Here we have 2 different waves, but they have the same wavelength, just different amplitudes. So light like this would be the same color, but one is brighter than the other. We can also talk about the frequency of a wave. So frequency is how many waves would pass a given point in a particular amount of time. So a common unit is hertz, Hertz, abbreviated capital HZ, which is the same as cycles per second or things per second. Sometimes it's just per second. So the number of waves would equal the number of cycles. So if you're standing, say, in the surf, and you've got these waves coming in from the ocean, the frequency would be how many waves hit you in a given amount of time. Now there you probably wouldn't measure it per second because it'd be less than 1, but perhaps in 10 minutes. How many waves hit you in 10 minutes? Okay. The total energy of the wave is related to the amplitude, how tall it is, and the frequency. And we can understand this thinking about ocean waves as well. If you're standing in the ocean and the waves are not very high, they come and they hit you and you're like, yeah, I got hit by a wave, right? But what happens if you get a really, really big wave? Maybe it's 10 feet tall and it comes and hits you. Are you going to notice that? Yeah. It has a lot of energy. It's going to knock you flat, right? So the amplitude is related to the energy. Higher amplitude, higher energy. And then the frequency also. So if you're standing there and a wave comes and hits you like every 2 minutes, like, yeah, no big deal. But what if the waves are pounding on you one every second? That doesn't happen in the ocean, but you can imagine. You're just going to be pounded on, right? And you're going to get tired of standing there because all of this energy from these waves is crashing on you. And the same relationship with light, that the higher frequency is more energy and larger amplitude is more energy. Now, in chemistry, we don't really deal with the amplitude very much, but we do think about the frequency and the wavelength. There's a relationship between the frequency and the wavelength because all light travels at the same speed. So if it's traveling at the same speed, then the wavelength and the frequency are inversely related. So we've got this relationship. The frequency is equal to the speed of light divided by the wavelength. So if you imagine, no, that doesn't work. So if you imagine, 2 people standing in the water, right? I have to draw it backwards. if these waves are traveling at the same speed, which of these people is going to get hit more frequently? A or B? A, right? They're going at the same speed. This one's going to go bang, 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 bang. And this one's going to go bang, 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 right? So the frequency, how many times you get hit per second, is related to the wavelength, the distance between the waves, because they travel at the same speed. So if the wavelength is small, then the frequency is high. If the wavelength is long, then the frequency is low. Does that make sense? So the color of light is determined by its wavelength or its frequency. They are related. What we refer to as white light is a mixture of all the colors in the visible light spectrum. When we say spectrum, we mean there's a continuous variation of wavelength. So here we have a prism, white light going through the prism. Because of angles of reflection and how the light travels through this prism, the light gets bent different angles based on the wavelength of the light. And so the prism separates this white light that has all the colors in it into individual colors, and we see what we call a rainbow. In a rainbow, the colors are always in the same order: red, orange, yellow, green, blue, indigo, violet. And one way to remember that is Roy G. Biv. It's like some very strange name. Red, orange, yellow, green, blue, indigo, violet. So red, orange, yellow, green, blue, indigo, violet. So when a child, what's up? When a child draws a rainbow, they often get the colors out of order. And so we look at that rainbow and we know what they're trying to draw. You know, it's got a curved shape, it's got lots of different colors in it, but we're like, what is not quite right with this? The colors aren't in the right order. So if you want to, draw accurate rainbows, Roy G. Biv. So when white light hits an object, so here we have light hitting this woman's shirt. Some of the light is absorbed by the shirt and some of it is reflected. And which things are absorbed or reflected depends on the chemical nature of her shirt. So a lot of these colors are absorbed, and because her shirt is red, I know that it is reflecting red light. The red light is reflected off the shirt, it comes to my eyes, and my eye interprets that as the color red. Her blue jeans are probably absorbing the red light and the green light and the yellow light, and they're reflecting the blue light. We've got many, many different colors that are possible because it can reflect some of the yellow and a little bit of the purple and a lot of the blue, and those combinations are going to give us different hues. So, fun to talk about rainbows and colors, and then we wreck it by making you do a calculation. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. Well, the frequency of light is equal to the speed of light divided by its wavelength. The speed of light is 3.00 times 10 to the 8th meters per second. And we need to divide this by the wavelength. We're told that the wavelength is 515 nanometers. If I put nanometers in here, the units aren't going to work out. I'm going to get meters per nanometer second. And what I want is just per second. So I could put this in here, but the units aren't going to work out. A very fast way to change this into meters is just to make use of what does the N stand for. Nano stands for times 10 to the minus 9. So instead of writing the prefix nano, I can write times 10 to the minus 9. So I'm going to take my 515 nanometers, and instead of nano, I'm going to write times 10 to the minus 9 meters. That is not in standard scientific notation, but your calculator understands it, and so it'll work just fine. So 3 times 10 to the 8th divided by 515 times 10 to the minus 9. The meters are going to cancel out. I'm going to get 5.83 times 10 to the 14. The units are 1 over second. That can also be expressed as s to the minus 1. And what that means is that 5.83 times 10 to the 14th wave crests pass in 1 second. That's a lot. Any questions? So visible light is part of the electromagnetic spectrum, but there's a lot of other types of radiation there, things that are higher or lower in wavelength than visible light. And we can't see it because our eyes are not equipped to detect things that are outside of the visible region. So shorter wavelength is going to have a higher frequency, and that's higher energy. So the shorter wavelength is going to be things like gamma rays. Those have higher energy than visible light. Things like radio waves are also electromagnetic radiation. They have very long wavelengths, very low frequencies, and very low energy. So high energy electromagnetic radiation can damage biological molecules, and it can do so by ionizing the molecules, so making a molecule into an ion, knocking electrons off. It's called ionizing radiation, and it's damaging, and it can actually kill you. So here is the electromagnetic spectrum as pictured in your textbook. It's a very common way of showing it. We've got a lot of information in here. Here we have a line showing different frequencies in hertz. Hertz is per second. Here we have a line showing corresponding wavelengths in meters. And then here we have the names of these different regions of the electromagnetic spectrum. This end is lower in energy, and this end is higher in energy. Sort of in the middle here, there's a very narrow region that is visible to the human eye. That's the visible light. That's a very important part to us. And so in this graph, what they've done is they've taken that little tiny section and they've expanded it so that we can see it better, right? So this is the wavelength in nanometers, 750 nanometers up to 400 nanometers. But that all is in this little tiny part here. Students often misunderstand what this diagram is showing. The red light is not lower in energy than microwaves, okay? Because this red actually belongs in here, okay? Violet light is not more energetic than X-rays, okay? We're going to do experiment 7A, and it's going to ask you about some stuff like this, and some of you are going to misunderstand the diagram and get the answers wrong. So I'm just warning you about that. Violet light actually belongs right in here. So we've got radio waves, microwaves, infrared radiation, the visible light, ultraviolet radiation, X-rays, and gamma rays. Your book has sections about each of these, and I think you should read about them. I'm not going to test you specifically, but we should have this order in our heads. So I'm just going to show you how I remember this. So I just kind of draw a line here. And I remember Roy G. Biv. So there's my visible light. Next to red light is infrared. It means below red. So this is the infrared. It's next to red. And next to violet is ultraviolet. It's like super violet, right? So UV is over here. Infrared light is, or radiation, is what's given off by warm objects. So if you've ever been to a hotel where they have that weird kind of reddish light in the bathroom and you turn it on, it doesn't give off much light, but it sure warms up the bathroom. It's giving off infrared radiation, and its purpose is to just give off heat. There's a little bit of a red glow to it because it is very close to this red visible light, but it's mostly infrared radiation. Ultraviolet radiation, we should all know, is what gives us a sunburn. So I remember sunburn, that's what burns you, something with higher energy. So that tells me that this end is higher energy. And the other end is lower energy. After ultraviolet, there's X-rays, which are useful for checking out your teeth or your broken arm. And then there's the gamma rays. Gamma rays are really dangerous. And then over here below the IR, there's microwaves. And yes, that is what's in your microwave oven. And then you've got the radio waves. So then how do you remember which end is high frequency or low frequency? Well, I imagine, or I actually draw a picture of two waves. There's the wavelength. So I can clearly see that this is a longer wavelength, right? Imagine standing in the surf and these waves coming and hitting you. Which one's going to pound you more? They're moving at the same speed. This one at the bottom. And if you look at them, this just looks more energetic, doesn't it? It looks like it's just jumping up and down, and this one like, right? So this is high energy, that's low energy. So then I can label this at the high energy. That's where I have the short wavelength, the high frequency. And at the other end, I've got the long wavelength and the low frequency. You will not be expected to remember any of the numbers on this chart, but we should be able to just draw a very simple spectrum like this, just putting the regions in order and identifying higher or lower energy frequency or wavelength. So we can use a prism to separate light according to its wavelength. If we take white light and we run it through a prism, it will separate it and we get a continuous spectrum. We get a continuous rainbow. We've got light at all of these different wavelengths. This is a picture I took. Yes, that's me and my daughter a few years ago now. We got to take a field trip to the Jet Propulsion Lab down in Pasadena, NASA's Jet Propulsion Lab. And they had this cool camera. So this is showing infrared light, and this is showing visible light. We can't see infrared radiation, But we can make cameras and other sensors that detect that radiation, and we can use those to generate pictures on a screen that we can see. And so we look at this picture and we can see that where our skin is exposed is red, that's warmer, and then yellow is a bit cooler, hair and clothing, and then in the background it's even cooler, it's a blue, right? And my phone is warm because I was taking a lot of pictures. That's infrared light. Infrared light can be used for thermal imaging, so you can take pictures of warm and cold. It's useful for finding living organisms in the dark. So night vision goggles use this technology and allow you to see warm things in a background of cooler things. High energy radiation is dangerous, but it can also be used for good. There's a technique called gamma knife, which can be used to work on tumors that are inoperable. You can have a tumor in your brain, and yeah, they could go in and cut it out, but in the process of doing that, they would damage your brain so much that you'd be worse off than if they just left the tumor. So what do? You can't cut in there. So they can use gamma radiation to get in there and zap the tumor. Now, as the radiation goes through healthy tissue, it damages the healthy tissue. So instead of just taking one beam and blasting a hole, basically, right, and making a dead part in your brain, they could do that with a knife. They take this and they come from multiple directions. So they're causing a little bit of damage through the healthy tissue, but it's all focused on the tumor. And so the tumor gets a lot of radiation, and you can damage the tumor, you can shrink the tumor, and only do a little bit of damage to the healthy tissue. And that's a lot about what medicine is balancing benefit and risk. Waves can interfere with each other. They interact, and we can have constructive interference or destructive interference. If we have two waves that are in phase, meaning that their crests line up and their troughs line up, they add together. It's called constructive interference, and the amplitude gets much larger. This is the effect that happens on a trampoline when you bounce just right and you can send your friend sky high, right? Because you're combining the energy to get a larger amplitude. If the waves are out of phase, this trough lines up with that peak, then these have destructive interference, and if they're lined up perfectly, they will completely cancel each other out. This can happen on a trampoline also, when you're just exactly out of sync and you bounce and nothing happens. Like, wait, how did that work? This is also how noise-canceling headphones work. So noise-canceling headphones take the sound in from your surroundings and shift it slightly and add it back in, and then it cancels out the noise and you don't hear anything. Pretty awesome. So constructive and destructive interference. Another thing that waves do is diffraction. When traveling waves encounter an obstacle or an opening in a barrier that's similar in size to the wavelength, they can bend around it. Traveling particles don't do this, but waves do. So the diffraction of light through two slits separated by distance comparable to the wavelength results in an interference pattern. And that interference pattern is a characteristic of all light waves. So here's an illustration of what we're talking about there. So here we have waves coming at a barrier. The slit here, if the slit is too small or too large, you won't see this. It needs to be about the same size as the wavelength of this light. So the wave comes here, and as it hits this barrier, it diffracts, and what you get is a curved wave that's coming through. Particles don't do that. When particles hit the barrier, they just either stop or bounce off. If they hit the slit, they just go straight through. So particles and waves behave differently when they encounter a slit. We observe this with light waves. You can also observe this with waves on water. Which brings us to the double slit experiment. So if we take a light source, we've got a single light source, and those waves are hitting two slits. Because this light came from the same source, it is in phase. As it hits the slit here, it diffracts, and over here, it diffracts. And these new diffracted waves are going to come across, and they're going to interfere with each other. In some places, they're going to be out of phase, and so we'll get a dark spot. In other places, they're going to be in phase, and they're going to make a bright spot. So as the light comes through, instead of just two lines on this screen, we're going to see a series of bright and dark lines. And it's from the light interfering with itself. And we've got another YouTube video here. This is one of my favorites. There we go.
What is light?
What is light? What is light? That's a good question. What is light?
Isn't it an element?
Light is brightness, I guess.
You have auras,
We all have auras.
which are light.
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right?
Yeah.
It would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances, besides the fringes of colors on each side of the shadow. The shadow itself was divided by similar parallel fringes, small dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I've never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
You can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box. Two bright bands.
Two little lines.
Linear.
Yeah, I think it'll be one line instead of two.
I could expect to see the whole box lit up.
That can be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two are the same.
The two on the outside are multicolored. The one in the middle is just white.
Kind of a rainbow.
The rainbow of colour as well.
Quite a few colours, but lots of little dots.
Like there are more dots appearing.
I think I can even see more dots. spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
2 slits.
2 slits. That's incredible.
Well, all we're doing is we're putting a light through 2 very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there. The average person's not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see 2 bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the same
And they go and
pattern.
overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and a bright spot, and a dark spot, and a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
that's
that's
because
working.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference
So
between
there's
red
so
and blue,
that red bin over there, the green part is just, I'm seeing
It's a
that
different-
it's just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
exactly.
That's amazing. I'm amazed. Oh, good on you, thanks,
Hey,
Ben.
thank you.
I have been enlightened. Literally.
Any questions? That's pretty cool, huh? I really love how he does this with the on the pond, because you can see the constructive interference here and the destructive interference, and that is what waves do. Particles don't do that. Any questions or comments? So what he's looking at on the bottom of the box is an interference pattern like this. Because that was white light from the sun instead of just light and dark, you've got light and dark right in the center, but the wavelengths of the red and the blue and the green are different, and so that's the rainbowing effect that you get as it spreads out. So, light is a wave, but it was also determined to be a particle. So, the photoelectric effect is what's observed when you shine a light onto a piece of metal. Many metals will emit electrons when you shine a light on them. Classic wave theory said, well, that's just because the light energy is being transferred to the electron, and once it gets enough energy from the light, then it will be ejected. So it's just depending on the amplitude or the intensity of the light. Higher intensity light, you're going to get more electrons. This idea predicts that there's a lag time. You shine the light, and then you need to wait a little bit until enough energy accumulates for the electron to be ejected. Here's a sort of setup for the photoelectric effect. You've got a metal surface, you shine light on it, and electrons are emitted. Now, the way that you can detect the electrons is you have all of this occurring in an evacuated chamber. You've got a voltage source, there's a positive terminal here, and you've got a negative charge on the metal surface, so that when an electron is released, it's repelled by the metal surface, it's attracted to this positive terminal, and we're going to measure the current. Current flow is the flow of electrons. So here is the sort of data that you get from an experiment like this. The rate of electron ejection is a function of the frequency of light. So you shine light with a low frequency, nothing happens. There's no electrons ejected. It doesn't matter how long you wait. Nothing happens. You won't get any electrons ejected until you get to this threshold frequency. There's a minimum frequency required to eject electrons. Once you hit that, you essentially get a constant result at higher frequencies. Same number of electrons per second. There is a difference due to intensity. You'll get more electrons with higher intensity than low intensity, but it doesn't change the threshold frequency. So what this says is that light is acting as a particle, not as a wave. To explain this, Einstein proposed that light energy was delivered to the atoms in little packets, particles or pieces of light. Those are called quantums or photons. The energy of a photon, a piece of light, is directly proportional to its frequency. So it's inversely proportional to its wavelength. There's a proportionality constant involved. It's called Planck's constant. It's given the symbol lowercase h. So we can say that the energy is equal to a constant times the frequency. Energy is equal to a constant times the speed of light divided by the wavelength. Planck's constant has this value. I'll give that to you on an exam, 6.626 times 10 to the minus 34 joules seconds. So the idea here of light being particles, the frequency of the light, high frequency is higher energy, low frequency is lower energy. So if I'm shining light with a low frequency on this metal, these particles do not have enough energy to dislodge an electron. Once I get to this threshold frequency, now my light photons do have enough energy, and each of them will eject an electron. There's no lag time. We can calculate things. A 100-watt light bulb radiates energy at a rate of 100 joules per second. A watt is defined as a joule per second. If all of the light has a wavelength of 525 nanometers, how many photons are emitted per second? So this is a dimensional analysis problem. So we've got 100 joules per second, and we've got 525 nanometers. Let's just write that as meters. That's our wavelength. Well, we can calculate the energy of one photon. The energy of one photon is going to be equal to Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. 6.626 times 10 to the minus 34 joules times seconds. That is h, Planck's constant. And we've got the speed of light, 3.00 times 10 to the 8th meters per second, divided by the wavelength, 525 times 10 to the minus 9 meters. The seconds cancel, the meters cancel, we're left with joules. 6.626 EE minus 34 times 3 EE 8 divided by 525 EE minus 9, 3.7862 times 10 to the minus 19 joules. That's the energy of one photon. It's very small. So if I want to know how many photons are emitted per second, this is a rate, joules per second. How many photons do you need for 100 joules? Well, this is, one photon is this many joules. Got one, oh, let's just do it this way. So I've got 100 joules per second. I want to end up with photons per second. So I'm going to change photons, or change joules into photons. So one photon is equivalent to 3.7862 times 10 to the minus 19 joules. So I can change the joules into photons now. My units are photons per second. So 100 joules divided by that crazy number gives me 100 divided by 2.64 times 10 to the 20th. Photons per second. Anybody else get that number? That's a lot of photons. Yeah?
Are you going to give us the 6.626 times 10 to the negative
Yes.
34?
Planck's constant, I don't expect you to remember that. I don't expect you to remember the speed of light either. And I'll actually give you equations like this. But you need to know what lambda is and what h is so that you can find it on the paper. This is the sort of thing that I was talking about in terms of the spectrum of electromagnetic radiation. Arrange colors of visible light in order of wavelength, frequency, and energy per photon. So it's asking us to arrange these in order of increasing wavelength. In order of increasing means you start with the small and you go to the big. A lot of people get this exactly backwards. I'm not sure why. Increasing means you start with the small and you increase as you go across. So for wavelength, we're going to go with small wavelength at the beginning and large wavelength at the end. Increasing frequency, small or low frequency to high frequency. Energy per photon, low energy to high energy. There will be questions on the exam that say, here are these things, put them in order of increasing or decreasing something. So we can answer this without looking at the spectrum, because we can draw our own here. Remember Roy G. Biv. Roy G. Biv. At the far right side here, I've got violet. Next to violet is ultraviolet. Yes?
What shape is that under the frequency small so much above the V?
It is the Greek letter nu.
Oh, okay.
It's a V with that's kind of curved.
I'm not sure how I'm supposed to draw that, or how to
Yeah.
pronounce that.
Yeah. So it's a straight line and then a curved line. It looks very similar to a lowercase v, which is really unfortunate because v is velocity and nu is frequency.
Yeah, that's how I was reading it.
Yeah. So thank you for asking. Okay, so we got Roy G. Biv. Next to V is ultraviolet. Next to R is infrared. Right? Kind of makes sense. Which of those gives us a sunburn? UV. Right? So this must be high energy. Right? And the other end is low energy. So I don't have to answer this question A, B, C. I can answer C first. So if I want low energy to high energy, and the colors I'm looking at here are red, green, and blue. So there's red, green, and blue. Which of those three has the lowest energy? Red. Right? So it's red, and then green, and then the blue. So red is lower in energy, blue is higher in energy. I put them in order of increasing energy. So then I've got wavelength and frequency. And so then in my head, if not actually on the paper, I'm going to draw myself pictures, right? High energy, right? Low energy, long wavelength, short wavelength. So if I'm looking at wavelength, small wavelength, red, green, or blue? Smallest wavelength? Blue. Right? So blue, and then green, and then red. What about frequency? Well, which of these is higher frequency? This one or that one? This is higher frequency, right? Frequency and energy go together. The wavelength is opposite. So high frequency is going to be the blue, low frequency is going to be the red. So this is going to be red, green, blue. Are we ever going to have a situation where it's going to be like green, blue, red? No. Because green is between red and blue in wavelength, in energy, in frequency. Any questions? So back to the photoelectron effect, photoelectric effect. We've got those ejected electrons. So one photon at the threshold frequency has just enough energy to dislodge one electron. So it does that. Psi is the binding energy of the electron. Looks like a zero or an O with a line through it. That's what we use to represent the binding energy of the electron. So in order to kick that electron out, the photon has to have that much energy, just enough to get rid of it. If we bring in a photon with more energy, what happens is you've got the energy of the photon, and you subtract the binding energy, the amount of energy needed to kick out the electron, and you've got some extra energy. That extra energy becomes kinetic energy of the ejected electron. So I think about Disneyland when I think about this. Anybody else thinking about Disneyland right now? This doesn't make you think about Disneyland? Okay, so the photon is a little boy, little girl, going to go to Disneyland. And they keep changing the prices, but I'm just going to say $100. Costs $100 to get into Disneyland, right? So what if you show up and you've got $85? Are they going to say, oh, well, you can go in for 8.5 of a day? No, sorry, no deal. You have to have that minimum amount to get in. What if you have $200? Are they going to let you in? Sure. Are they going to take all $200 at the gate? No, you give them $100. And you still have $100. What do you do with that? You go inside and you blow it on overpriced stuff, right? You know, $10 chicken nuggets and a $500 t-shirt. You know, it's just crazy in there. So the photon comes to the metal. If it has the right amount of energy, it can eject the electron. If it doesn't, nothing happens. If it has more energy, it ejects the photon, and the extra energy goes with the photon. Kinetic energy is just going to be moving faster. It's the speed of light. It's not going to go faster, but it's going to have a higher frequency. So the excess energy becomes kinetic energy of the ejected electron. Any questions? We would not see this effect if light were only a wave. But light also behaves as a particle. And that's where we get into this dual nature. Light is particles and waves at the same time. But when you observe it, you force it to act like one or the other, because you can't observe them being both at the same time. So suppose a metal will eject electrons when struck by yellow light. What happens if it's struck with ultraviolet? Well, we need to know, is ultraviolet more energetic or less energetic than yellow? It's more, right? Roy G. Biv, and next to violet is ultraviolet, and that's higher energy. So ultraviolet is more energy than yellow light. The yellow light has enough energy to eject electrons. So if we're sending in particles with more energy, are we going to get no electrons ejected? No. Electrons would be ejected and they would have the same kinetic energy as those ejected by yellow light. No, because our ultraviolet photon has more energy than yellow. That energy has to go somewhere. The electron gets it as kinetic energy. Electrons would be ejected and they would have greater kinetic energy than those ejected by yellow light. That's the correct answer. Electrons would be ejected, but they would have lower kinetic energy. So the kinetic energy is like the spending money that the photon has, right? Or the electron. Any questions? So sometimes light acts like a wave, sometimes it acts like a particle. And what you observe depends on the particular experiment. You can't observe them both at the same time.